so much to the organizers for giving me the opportunity to talk to you here today. So I am much more on the applications side than on the pure machine learning and statistics side. So I'm kind of hoping that this is going to be a bit of a two-way conversation in this talk. So I know that this is the second last talk of a very, very long 2 weeks. The program is quite intensive, right? So everybody's probably feeling a little bit tired. Okay, so this talk is going to be something a bit different from what you're used to over the last 2 weeks, and I hope you enjoy it. So I'm only going to actually talk for about half of the 90 minutes that I've been allocated. You guys are going to talk for the rest of it. So I'm going to start with a little bit of introduction, something you probably don't know too much about, specifically to do with cosmology. Okay. In 1917, the great Albert Einstein made a terrible mistake. He called it his biggest blunder. It's hard to imagine such an amazing person making a mistake, but it's true. So Einstein is, of course, famous for the general theory of relativity. So this basically was the key that unlocked our understanding of gravity. For hundreds of years, people, including Newton, had worked on trying to understand not just how gravity works, but what it actually is. And it was really Einstein who figured it out. And it's, in my opinion, one of the most beautiful theories in physics. It can be encapsulated by this deceptively simple equation. These are called the Einstein's equations. There are actually several equations in here in disguise in this tensor form. And colloquially, the way we talk about it is, on the left side of the equation has to do with geometry. How does space-time, what is the geometry of space-time? And on the right-hand side of the equation has to do with the stuff in the universe, the matter and energy content of the universe. So we always say colloquially that space tells matter how to move, matter tells space how to bend. That's kind of how general relativity works in a kind of hand-wavy way. So what was the mistake that Einstein made? Einstein's equations implied that the universe was dynamic, that space could be expanding or could be contracting. And he didn't like this. At the time, it was thought that the Milky Way was basically the whole universe. And it was thought that the universe was static. And he so deeply believed what was conventional wisdom at the time that he did what every good scientist would do, or not so good scientist, he added a fudge factor. This fudge factor has become known as the cosmological constant. And by introducing this constant into the equations, he could force the universe to be static. Now, just a few years later, some observations came out that made Einstein retract this fudge factor and call it his biggest blunder. These observations looked like this. And before I discuss the observations, I wanted to mention kind of the story behind them, because it's quite interesting. This very simple linear law is known as Hubble's law. And the constant of proportionality in this line is called the Hubble constant. This is remarkable because Hubble was not the first person to propose that the universe was expanding. He was not the first person to say, actually, Einstein's equation do imply an expanding universe. And what's more, these aren't even his observations. These observations were taken by a guy with the unfortunate name of Vesto Slipher. And from what I've heard, the key difference between Slipher's results, which he published with the same data, and Hubble's results was Slipher put his observations in a table, whereas Hubble made a pretty picture. So there's two lessons, I think, from this story. One is credit is very rarely correctly assigned. And the second is that if you have a choice when writing a paper between putting your results in a table and making a pretty picture, make a pretty picture. You might get something named after you and be famous for 100 years. Okay, so what are you actually looking at here? So what Hubble did was he looked at galaxies. Now, at the time, they called them extragalactic nebulae. They didn't really know what they were. There was still a great debate raging on whether our Milky Way was just one of many galaxies and the universe was much bigger than we thought, or if conventional wisdom was right, and these funny objects were not actually that far away. But in any case, what Hubble did was he looked at these objects, whatever they were, and he tried to figure out the distance to them. This is difficult, but basically what he did is he assumed that all these objects were basically the same, and that the things that were fainter were further away. A reasonable assumption. What he also did was he measured the velocity of these objects, which you can do by taking a spectrum, which I'm going to talk about a little bit later. So he measured the velocities of these objects. And what he found was this pretty clear relationship that things that were further away were moving faster away from us. And the key thing here is that all the galaxies were moving away from us. So barring just a few galaxies that are very, very nearby, every galaxy in the universe is receding from us. And this is actually kind of strange. It's very difficult to explain this without the explanation that space itself is expanding and Einstein's original equations were correct. So here's a cartoon of it. If you imagine each of these stars is actually a galaxy. The galaxies aren't moving. The space itself between them is getting bigger. And so you can see that if I pick one of these stars and I say that's the Milky Way, and I look around me, all the other galaxies are going to be moving away from me. So okay, after these observations, it was pretty much accepted that the universe is expanding. This was good evidence for the Big Bang model, and there was much more evidence that came later on. And for just under 100 years, we were happy with this. The universe is expanding, and it all kind of makes sense. In 1998, some more surprises were in store for us. So this plot is basically an extension of that Hubble diagram that I showed you before. The axes have been swapped around. This is effectively a proxy for distance, and this is now the velocity. And what you notice is that nearby, things look pretty linear. Things look like what Hubble saw. But if you go a bit further away, something funny starts to happen. Okay, before I start talking about this something funny thing, I want to talk about how we get these points. Because this is now much, much later, and we've gotten much better at measuring distances. Cosmology is really all about measuring distances. It makes sense. If you want to study things on the largest scales, you've got to try to get accurate distances. And we use an interesting tool to measure these distances. We use a tool which is the death of a star. So those points that I showed you on that plot, each one was a supernova. Death of a star. These explosions are the most energetic events in the universe. For a few days, a single star will outshine an entire galaxy of 100 billion stars. That's how energetic this explosion is. The cool thing about supernovae is we can use them as standard candles. Okay, what's the idea behind a standard candle? If I took a light bulb and I said, this is a 100-watt light bulb, and I went away some distance, you could measure the brightness of that light bulb, and because you knew how bright it should be, you could figure out how far away I am. That's the idea behind a standard candle. It's an object that we think we know what the intrinsic brightness is. And supernovae can be used like this. So if we find them in galaxies, if they're very faint, it does actually mean that they're very far away. Now, there's a problem here. I just gave you the example of the 100-watt light bulb, right? What if I gave you a 100-watt light bulb, I told you it was 100 watts, but it was actually only 60 watts? What would happen? You'd get the distance wrong. So that's the problem. There are actually different types of supernovae in the universe, and only one of them is useful for cosmology. There are actually more types than these that I've explained here, but these are the kind of most important ones. There's the core collapse supernovae, which is like that animation I just showed you. This is a massive star, runs out of fuel, collapses in on itself, and explodes. Core collapse supernova. But there's another type, which is a little bit more complicated. There'll be usually a white dwarf here, and then it'll have some companion, either a normal star or another white dwarf. and we're not actually sure which, probably both, actually. But the point is that if the star accretes matter from its companion and hits a certain critical mass, it explodes. And this is the key point. Because it always explodes at the same mass, it must explode at the same brightness. Obviously, there's caveats to that, but in general, this is the thing that makes a type 1a supernova a standard candle. These things can explode at any kind of mass. It depends on the astrophysics of what's actually going on. So to us as cosmologists, these are contaminants. And this is going to be important when I talk about machine learning later. I promise there is machine learning in this talk. But we got to build up some introduction first. Okay, so now you understand what supernovae are, you can understand this plot. So these distances are actually much, much bigger than the ones that Hubble, Hubble obviously didn't have access to the amazing telescopes we have today. So these groups in 1998, there were two independent groups, were able to take observations of very distant galaxies. And so these two independent groups took observations, observed some supernovae, and found this weird thing. It's very small. It looks like a very small effect. But you can see that if you took the difference of these points from just a linear fit, there's a little excess here. That little excess implies something quite remarkable. It implies that the expansion of the universe is accelerating. Why is this so strange? It's a little bit like if I was to push you on a swing and stop pushing. What would happen? You'd eventually slow to a stop because of friction. Now imagine I pushed you on a swing, and instead of slowing down, you just swung faster and faster and faster until you flew off. That's what the universe is doing. It doesn't make a lot of sense. We expected this expansion to be slowing down, to be contracting, eventually. But it's doing the opposite, it's speeding up. And there is nothing in our laws of physics at the moment that can really explain this, except Einstein's biggest blunder. So it's kind of funny that 100 years later, we brought back Einstein's cosmological constant to try and explain this accelerated expansion of the universe. Okay, so this is a snapshot of the history of the universe. This is our model of cosmology, the whole universe in one picture. So what this is trying to illustrate is the expansion of the universe. And for a good number of years, it's just this kind of constant expansion is doing what you expect, until dark energy starts to dominate about 4 billion years ago and causes this accelerated expansion. So we call this thing dark energy because we don't really know what it is. It could be some kind of energy, some kind of weird, mysterious material causing this accelerated expansion, or it could be something else. The embarrassing part is this is a pie chart of the universe, the stuff that makes up the universe, the energy density of the universe. This bit is all the stars and galaxies and dust and gas and planets and people and plants and animals. It only makes up 5% of all the stuff in the universe. So all the things that we actually understand, more or less, is only 5%. 27% is something also quite strange called dark matter, something that interacts gravitationally but not in any other way. It doesn't emit any light, it doesn't reflect any light. And 68% is this dark energy, which is even worse than dark matter, in that it does something completely bizarre, causing this accelerated expansion. So this very surprising discovery awarded 3 people who were leading the different teams the Nobel Prize a couple of years ago. And we are now 20 years on from that initial discovery, and we still don't know what dark energy is. Yes? Yes. I didn't talk about dark matter. So dark matter is something quite different from dark energy. We just put the word dark in front because we don't understand it. So, yeah, I mean, we're astronomers. We're not really good at naming things. I'll give you an example later. So dark matter, we think we understand a little bit better than dark energy. it seems to behave a lot like normal matter in terms of its gravitational effect, right? But it doesn't do anything else. It doesn't emit any light. It doesn't reflect any light. So there's no electromagnetic component. We only know it's there because of indirect evidence. It does funny things to galaxies, to the stars and galaxies. They're moving faster than they should be. There has to be some kind of matter in there to explain that. We also see evidence for it in various cosmological probes. We couldn't actually get the structure of the universe that we observe without dark matter. So it's something we know is there. You know, it's a little bit like air. We can't see air, but we know it's there because we're still alive and breathing. You know, we have evidence for it. So dark matter is just a normal matter, and it operates gravitationally, which means it attracts, just attracts other matter. Dark energy is something else, something quite weird. It kind of does the opposite effect. It's causing the expansion of the universe to go faster and faster, which means it's pushing stuff apart, effectively. But the only way that it operates is on space itself, as far as we can tell. Does that answer your question? Okay. Yeah? Oh, wow, that's a really good question. I don't actually know. Ah, yeah, that's also a good question. The speed of light is the upper limit, right? So how can it... So what's interesting is you can actually cheat with that rule. This bit of the universe, this inflation, the universe itself is actually expanding faster than the speed of light. That's another period of accelerated expansion. You can cheat because the rule about the speed of light comes from information exchange. The information cannot travel faster than the speed of light, but it's space itself that's expanding, and so there is no information exchange. So you can kind of get away with it a little bit. So as far as we know, because there already has been this period in the universe where we believe the universe accelerated incredibly quickly, there doesn't seem to be an upper limit to this accelerated expansion. Of course, this is not something we experience on this scale. On the scale of Earth, on the scale of the solar system. This is on the scale of, you know, not even galaxies, clusters of galaxies. On very, very large scales, it becomes important. But in terms of the exact number, how fast are galaxies moving apart from each other, how much more fast every year, I don't know. I'll look that up. That would be a useful thing to have. So, do you know offhand?
About 1 centimeter per second squared for an object that's a billion light years away.
So a billion light years away, an object goes 1 centimeter per second squared faster each year. The acceleration is 1 centimeter. Yeah. Yes, John.
Yeah, but the time scale for that is about the age of the universe.
Right.
So we're not going to lose the universe tomorrow.
Exactly. It's okay. You know? We're all still going to be here tomorrow. And for the well, actually, the way the world's going, I don't know if we're going to be here tomorrow. It won't be because of cosmology that the world ends. Let's put it that way. All right, so 20 years later, we're still stuck. We have this model that works really well. Ironically, bringing in Einstein's cosmological constant works. It explains, at least it fits the data, but we don't understand it. We don't really understand something that could cause this accelerated expansion, right? It's a little bit like how Newton found the laws of gravity, and it worked, and it fit the data, but he didn't understand them. He didn't understand the cause. And we have a couple of different models. There are models that basically say, okay, maybe there's some really weird, mysterious substance in the universe. That's kind of usually what we mean when we talk about dark energy. Some kind of strange substance that can cause this kind of repulsion. Or maybe Einstein was even more wrong, and we need to modify his equations. So those are modified gravity equations that often try to explain dark energy and dark matter. And you know, there's a couple of other ideas based on the geometry of the universe. But you know, nothing really is super compelling. The theorists are still working, trying to come up with stuff, but we're still pretty stuck. So what do? One of the things we do is try to find another way to poke at the universe. Cosmology is a little bit like archaeology or paleontology. You know, we can't really perform experiments. We can't go out there and prod at some galaxies or go back in time and see what happened. We kind of have to look for evidence in more indirect ways. So I already showed you a cosmological probe. It's called supernovae. We can use supernovae to figure out distances, and from that figure out at least what is the behavior of the expansion history of the universe. There are a number of different probes that we could use. One of them I just want to mention, partly because I get to show you a pretty picture, is growth of structure. This is also a very important probe of dark matter. So what you're seeing here is a simulation. We do these massive n-body simulations. We put in loads and loads of galaxies at the very early universe. We code up the laws of gravity. We let it run and see what happens. And you end up with pictures like this. So each of these dots is actually probably an entire cluster of galaxies. And what you see happening is just by matter attracting to each other under gravity, you naturally form this beautiful cosmic web pattern. Now, by measuring growth of structure, so that means looking for galaxies and looking as far back in time as we can go, because astronomers actually are time travelers. If you look at fainter stuff, you're actually looking into the past, just because light takes time to get here. It's kind of cool. But what that means is that if you observe galaxies, lots of galaxies far back in time, you can see how this clustering pattern changes over time. And how does that help you with dark energy? Well, remember I said dark energy it's kind of a repulsive thing. It's accelerating expansion of the universe, which means it operates against galaxies trying to attract to each other under gravity. So if you have stronger dark energy, more dark energy, it means you'll have less structure, less clustering, and vice versa. So by observing galaxies and doing some pretty good statistics on them, we can figure out how dark energy is affecting the universe, and if it's changing with time. That would be one of the key things. Okay. So how do we actually do this? Well, in astronomy, bigger is always better. So while the theorists try to figure out what dark energy is, us observers just go and build bigger and bigger telescopes to get more and more data, be more and more sensitive to tell the difference between different models. Actually, before I talk about telescopes, does anyone have any more questions on the cosmology? Okay. So I'm going to talk about two really exciting experiments that are being built right now. And these are really massive. They're going to do lots of different science cases, but they're going to be really great for cosmology. The first one is the Large Synoptic Survey Telescope. So this is an image taken a couple months ago. It's being built out in Chile. It's a US-led project, but it's a big international project, so lots of countries are involved as well. This thing is kind of insane. This is an insane telescope. Why? It's not that it's that big. It's an 8-meter class telescope. We've had 8-meter class telescopes before. But it has kind of, to me, magic optics, which means that whereas most big telescopes can see small patches of sky but go really, really deep, this thing can go really deep over a huge patch of sky. What it means is that it can observe almost the entire southern sky every 3 nights to quite a remarkable depth. And it's got a lot of science cases. One of the science cases is actually to monitor near-Earth asteroids. So I don't know if you guys heard about the meteor impact the other day. It blew up in the atmosphere above one of the local towns. So the idea is LSST is going to be able to observe quite a large number of these near-Earth asteroids. So at least if a big one starts heading our way, we can panic about it for a few years, which would be great. So, but one of the other major science cases is dark energy. So especially supernovae, it's going to be amazing for supernovae. So this will be one of the best telescopes for supernovae, which I'm going to talk about a little bit later. So trying to bring this back from cosmology into data science, I wanted to mention some of the data rates that we're going to be dealing with. LSST will detect 10 million transient events per night. This is just because it's got such a big field of view and it's so fast. 10 million times a night it's going to find something has changed. That's pretty massive. Now, the majority of that is going to be hot pixels in the CCD, cosmic rays, airplanes, junk like that. But even if 1% of this is astronomical, that's still a huge number of transient phenomena that we're going to need to sort through. It is quite obvious that there aren't enough grad students in the world to sort through this data. So we need machine learning, and this is a huge focus in LSST. And just in terms of the data rates, I mean, it's not enormous, but it's 13 terabytes of image data per day. So, you know, if you're used to kind of Kaggle challenges, I'm going to download it on my laptop and play around, you know, we're not in that era anymore. And a lot of astronomers are actually kind of a bit used to that, so there is going to have to be a bit of a shift in how we work with this data. Even crazier data rates will be the square kilometer array. So I'm pretty sure at least the South Africans in the audience probably have heard of this thing. This will be the biggest telescope ever built by quite a large margin. So the idea is to have 1 square kilometer of collecting area, which is enormous. It's a million square meters. And the interesting thing about this telescope is it's a radio telescope, so it works differently from an optical. So these dishes that you see kind of probably remind you a little bit of like your satellite TV dishes. It operates on exactly the same principle, except we're avoiding DSTV satellites and we're trying to look at the universe. There are 2 different components to this telescope. One is the mid-frequency component, which, you know, we kind of understand. It's kind of the normal way radio telescopes work. The other is this quite novel technology, which is the low-frequency component, which just kind of look like these bits of wire stuck in the ground, and there's going to be tens of thousands of them. And amazingly, through lots of quite clever hardware and software, you can actually do astronomy with this thing. So this bit's going to South Africa and is currently being built out in the Karoo. This bit's going to Australia and is being built out in the outback. In terms of data rates, SKA Mid, which has by far the lowest data rates of the 2, is going to produce over 100 petabytes of data per day. SKA Low is, I think, a factor of 100 more. So yeah, we might be a little bit screwed. So online automated data processing is obviously essential. We can't actually store this volume of data, which makes the scientists very unhappy. So a lot of effort is going into these analysis techniques, and a lot of effort is going into machine learning, especially in our group at the SKA. So I just wanted to mention MeerKAT, which is one of the precursor telescopes. So basically what happened is a few years ago, it was South Africa versus Australia, who's going to host the SKA. You know, it's a little bit like the Rugby World Cup or cricket, but it's astronomy instead. So basically the international consortium said to each of us, okay, we want to see that you have to prove that you can build a radio telescope, so I want you each to build a prototype. Which was interesting because Australia has a long and prestigious history of radio astronomy, and we'd never built a radio telescope. So what we did is we started building this telescope called MeerKAT, which had first light just last year. And it's a 64-dish telescope, so it's kind of a mini version of SKA Mid, but in its own right, it's one of the most sensitive, high-resolution telescopes in the world. So it's really holding its own on the international stage. And just to prove it, this was the first light image of this is the center of the Milky Way. One of the main reasons we like to observe in the radio is because optical light gets stopped by dust in the universe, and there's quite a lot of it, especially near the center of the Milky Way. If you look in the radio, it goes straight through that dust. So we can have a really clear view of all this activity going around the supermassive black hole near the center of the galaxy, which is really cool. This is touted as the clearest view of the Milky Way astronomers have ever seen. So, yeah, I'm pretty proud of MeerKAT. So, but the point, I should mention that MeerKAT also has quite high data rates. It's not on the petabyte level yet, but it's sort of tens of terabytes a day potential. So we're also looking at new analysis techniques, lots of machine learning, and we're going to have to do things quite differently. Okay, so now I'm actually going to do some machine learning. Some caveats to when you're applying machine learning to astronomy that may be a little bit different from some problems in industry and in other fields. We're pretty much always in the low signal-to-noise ratio regime, because even though there's quite a few bright objects in the universe, there's many, many more faint objects, and we want them. We want the faint galaxies. We want to push as deep as possible. So, you know, often for many machine learning problems, like telling the difference between cats and dogs, you've got pretty clear images of cats and dogs. But in this case, you know, it's like, is this fuzzy blob a spiral galaxy or an elliptical? It can be kind of hard to tell. So following on from this, uncertainties are always important, right? We have to be able to quantify how uncertain we are. And this is often where we struggle with some of the more traditional machine learning algorithms, because it can be difficult to pull out the uncertainties. Machine learning, following on from that, machine learning is only ever one step in the pipeline. It's not like we just need to do some classification and then publish and the problem is solved. Especially if we want to do cosmology. If you're classifying supernovae, the different types of supernovae, that sample of supernovae now goes into a complicated cosmological analysis. If it's biased, or if you have poor estimates of probabilities, it's going to cause problems down the line. And these analyses are very sensitive to these things. Okay, so these are just some things to keep in mind. So, now I'm going to do a little bit of an experiment, because I didn't want to stand up here and talk for an hour and a half. So I've talked for about half an hour, and now it's your turn. We are going to go through 5 of what I consider, and Bruce and I consider, some of the most interesting machine learning problems, open problems, active research areas in astronomy. I'm going to introduce the problem, and I'm going to try and keep it quite general and be able to just connect you to it without needing lots of domain knowledge. Then you're going to get into little groups and discuss this problem a little bit. Think about, is this similar to something you've worked on before, something you've read about? If you were given this data in a Kaggle challenge and you didn't know anything about it, what would you do? What would be your first steps? My hope with this is that we'll get 2 things out of it. I hope that the students will practice thinking about where to apply the things that you've learned over the last 2 weeks. But I'm also hoping that there'll be some new, fresh ideas coming from the audience. I've got my notepad out. I'm going to write down things that I haven't heard of. So I'm hoping that you guys can tell me about some stuff, and maybe we can go on and change the face of astronomy forever. You know, or not. Okay, so if you're... Okay. I think everyone's got people around them. Okay, let me introduce you to the first problem. Remember I said LSST is going to detect 10 million transients per night. This is an illustration of where each of these dots is a supernova. So, you know, every day, pretty much, there's at least 1 or 2 new supernovae. In fact, at the end of 10 years, we're expecting a sample of about 500,000 supernovae. To give you an idea of how cool that is, those original observations that showed that dark energy was out there, Adam Rees, I remember he gave a talk, the Nobel Prize winner, and he used to say that he could name every single supernova in his data set, because he had about 40 of them. Now we're going to have 500,000, right? So the constraining power of this data is phenomenal. But there's a catch. There's a problem. Do you remember I said that there are 2 types of supernovae and only one is useful? The problem is the only way to be sure of which one you've got is to take a spectrum. So if you remember in school, you did experiments where you put white light through a prism and it would open up into a rainbow. You're actually taking a spectrum. And so we have instruments that do exactly this, break light up into different wavelengths. There's a lot of information here, a lot of information about the chemistry of what you're looking at. And so it can tell you what type of supernova you've got. LSST can't do this. Can't take a spectrum. It's a photometric only instrument. It only takes images. So we have to follow up stuff that we're interested in with other telescopes that can do this. And the problem is it's expensive. It takes a lot of telescope time, especially if the object is faint. So that means we're only going to be able to follow up maybe at most 5% of the LSST data. And we don't want to throw it away. So obviously, enter machine learning. And this is just an illustration of what the data looks like. So this is a spectrum. If you look at this funny black line here, you can see all these dips and spikes. Those are actually atoms and molecules absorbing and re-emitting light. And that's how we can tell what the chemistry of the object is doing. But we don't have that with LSST. What we have is these kind of purple things here. These are filters. So if you're a keen photographer, or you maybe ever had an amateur telescope, you might have put a filter in front of it. It blocks out all light except for in a particular band. Okay? So we have a few of those. We've got 6 of those. Some are more efficient than others. These ones suck a little bit. But the point is that we can get images in 6 different filters at different times. So it's like a poor man's spectrum. Instead of having, a few hundred individual wavelengths or maybe thousands, we only have 6. Okay. So the data ends up looking like this. This is what example supernova, this is only in 4 different filters. But what happens is the supernova actually explodes. What you're actually looking at is radioactive decay. So it gets brighter and it goes fainter over 40 days or so. And you can see that different bands, different colors, have different features. The green one's kind of faint. The Z band has this kind of extra bump. And different types of supernovae will have different features, but they're very subtle. Even experts can't tell the difference. But there are differences, and machine learning can pick it up. Okay, so I want you to think about this as you've got time series data. Okay? One thing to remember is that these can explode at so they're not aligned, so they're not necessarily going to explode at the same point in time. But time series data in these different filters. That's your data set that you've got on Kaggle or whatever. So, how would you solve this? So what I want you to do is let's take this front row. You guys can just turn around and face the row behind you. Same thing for the 3rd row and the 5th row. Basically, just get into like little groups of about 4 or 5 and discuss, and I'll give you guys a few minutes, and then we'll come back together. Okay, right. Let's see what people thought. So if I don't get volunteers, I'm going to randomly ask people. So I want you to be interactive. So hands up, let's have some ideas. How would you approach this problem? I'm not joking. I'm gonna find the people trying not to look at me, and I'm going to pick you. Come on, some ideas. Yeah, go for it. Cool. So, yeah. So that's good. Yeah, I definitely like it. Learn from the LHC. One of the big differences between astronomers and particle physicists, though, so in the particle physics experiment, they'll throw away 1 million events and keep one. We can't do that. As scientists, we really care about these astrophysical events. What we are going to throw away is the things like the cosmic rays and the whatevers. So we absolutely do have to have that pre-filtering step, and it's run by what's called a broker that will run live on the data to pre-filter it. Okay, and then you mentioned a naive classifier, so we'll get back to that. Anyone else got some ideas? How would you approach this problem? Yeah.
We could maybe train a generative model that converts your photometric data to spectrum data on historical data, and then when we get new data in, we can do that transformation, look at the spectrum that we generate, and use a classifier to detect whether that's what we want or not what we want.
Nice, I like it. Generative model from photometric data generating a spectrum. It's because, of course, there's always a lot of information, so it will be consistent with a few different spectral models. So you'll have to bring in some kind of statistical method of incorporating that uncertainty. But very nice. What else? Okay, so you mentioned a naive classifier, some kind of just whatever, random forest, naive Bayes, cool, do something like that. But we have to select features, right? We all know that the feature engineering is the hardest part of the problem unless you're using deep learning. And the problem with using deep learning for problems like this is we actually just don't have the volume of data. So people have tried and have used simulations to augment the data, etc., but it's actually the more simple machine learning approaches that tend to work a bit better. So just to very briefly show you the stuff that we did for Supernovae, which has worked quite well, is we've looked at 3 different feature extraction methods. These are pretty domain specific. These are models for supernovae. They're empirical models. They're not real physical models, but they're models nonetheless that we could use and fit those parameters in our usual way. This one turned out to work quite well. This is a wavelet analysis. If you're not familiar with wavelets, it's kind of like a transform, but it keeps some localization information, keeps some spatial information. So it's great for non-periodic signals. If you do some time series analysis, which is non-periodic, it's a cool tool. And then we tried out a bunch of different machine learning algorithms and obviously found things like neural networks and boosted decision trees work the best. So this is a very sort of standard machine learning approach to this. I just quickly wanted to mention, does anyone regularly take part in Kaggle challenges? Or have you ever taken part in a Kaggle challenge? Cool. Have any of you seen this challenge on Kaggle? Plastic. Just finished recently. So this was actually, it was great. You know, we had over 1,000 teams taking part. We simulated expected LSST data, just like the one that I showed you, but for lots of different types of objects, not just supernovae. And basically asked the data science community to come up with approaches to solve this. I'm quite sad that an astronomer won, but it actually ended up taking a fair bit of domain knowledge to figure it out. Okay, next problem. I'm going to plow through into the next one. So one of the things that we did in plastic is we made sure that the training data was non-representative of the test data. Okay, this is a major, major problem in machine learning. Most algorithms just don't generalize well enough if your training data and your test data are not drawn from the same population. So here's an example of what the plastic data looks like. Kind of ignore this blob here, these are redshift errors. Just focus on the data here. This is, again, that same Hubble diagram I showed you. This is magnitude, so the brightness of the object, against redshift, so how far away it's, basically how far away it is. And the orange one's the training set. So you can see there's entire regions of faint, distant objects that aren't really covered in the training set. And now that may seem really unfair in a Kaggle challenge, but it's actually what we have to deal with as astronomers. Because spectroscopy is hard, we can't get these really faint objects. So our training set is going to be biased. And this is still a hugely active area of research in astronomy. Okay. So I would be really interested if you guys want to, again, turn around and discuss what experience you might have had in dealing with non-representative data. And even if you haven't, what kind of tricks could you think of in order to deal, or what do you know about, in order to deal with this non-representative issue? Yes, Hans? That's a good question. We don't even know in the Kaggle challenge if the test set that we had to work with was representative of the final validation set. In this case, this is as realistic as we can get. So this is really genuinely what we think LSST is going to find. So we think that the test set is representative of the real data, but the problem is that we can't follow up all of those objects. Does everyone understand what I mean by non-representativity? Non-representativity. Kind of nod if you understand. I've got some shaking heads. So let me just quickly say once again, in machine learning, in our typical machine learning problems, or in any kind of modeling problem, you'll have some subset of data, your training data, that you're trying to use to learn your model. And then you want to apply that model onto some unseen test data, right? Now, the problem with most traditional machine learning algorithms is that if your training data and your test data aren't drawn from the same distribution, if they aren't the same, then these algorithms don't generalize, usually. You know, it's a little bit like if I told you to tell the difference between cats and dogs, but I only ever gave you calico cats and poodles. And then in the test set, I gave you a Rottweiler. And now, you know, an algorithm has never seen this before. Okay, so please discuss with your neighbors and think if you've got any ideas. Yes, question. Do we know what we don't know? That's a really good question. So in this case, you know, I didn't know the types of the test set, but I could extract these features, right? So I could see from these features that they don't overlap. So think about it. So there's kind of two regimes. One in which you know the way that you are going to be non-representative, which is actually where we are here. We know how we're going to be non-representative. But then there's also the regime where maybe you don't know anything about your data, but you see that the features don't completely overlap. What can you do? Okay, go for it. I'll give you a couple minutes. Okay, let's come back together. Who's got some ideas? Any ideas? Yes. Yeah, good idea. So there are a couple of points, right? There's a few that are in the regime where there's very low coverage in the training set. You could upweight those, increase the importance of those points when training. Good. Any other ideas? Yes.
So in current risk, you often build on a certain population and it has to generalize well. So what we do sometimes is group the variables so that you don't have as many outliers. And you can use transparent algorithms that you can sanity check and make sure you think it'll generalize well. And then you can actually have a model that works really well on data that it hasn't seen before.
Cool. Do you have any references for me? Hey? Any references I can look at?
You can look at weights of evidence, grouping.
Weights.
Yeah.
Perfect.
Statistic regression algorithm can
Yeah.
there's others, but it's important that you can do a sanity check, and even something like this probabilistic programming is a nice way to put some domain knowledge into models that will generalize well.
Yeah, I think it's very hard to get away from needing domain knowledge in these things. Correctly. Good. Data augmentation. Good. Okay, so one of the main techniques that people have been thinking about in astronomy is data augmentation, which kind of combines the idea of upweighting training data in underdense regions, but then you need a way of augmenting the training set. So one that we use, which is quite nice, is actually to use Gaussian process regression as a model. So you can do regression on the training data and then draw new examples from that. And you can effectively oversample training objects in the underdense regions. If you have a lot of domain knowledge, you can actually use simulations. If you trust your simulations, you could simulate, for example, high redshift supernovae. But really, all of these do require quite a lot of domain knowledge. So I'd be interested in checking out techniques that maybe don't need as much. Cool. Next. This is my personal favorite at the moment, anomaly detection. So this is the most exciting part of science, is discovery. Discovering something new, something we don't understand, something unexplained. And LSST, SKA, with petabytes of data coming in, there's huge potential for discovery. But the way we've discovered things in the past has generally been a person, often a grad student, staring at the data and finding something strange. We can't do that anymore. We have to rely on new techniques, automated techniques, for finding the unknown. So here's an example. This thing probably looks quite similar to that supernova that I showed you before, although if you notice, the time frame is much shorter. They're only over a couple of days. But, in some sense it looks quite similar, especially in the beginning. It can look very similar to a supernova. But this is, in fact, the merger of two neutron stars, some of the most dense objects in the universe, producing one of the most powerful explosions in the universe. And these are very rare, and we really care about them. So we need to be able to find these in our 10 million transients a night. And even more important, so this is just a rare object that we know what it looks like. Even more important are objects that we have no idea what they're going to look like. So I would like you to think a little bit about anomaly detection. What kind of techniques are there? What have you heard of? What could we use? Think about this very generally, but if you want to think about a specific problem, you can use the transients problem. So again, time series data in these different bands, but some of them are going to look weird, and we need to find those. Okay, go for it. Think about anomaly detection. Okay, let's see how people got on. Who's got some cool ideas about anomaly detection? Hands up. Yes? Autoencoder, okay. So basically you're saying use an autoencoder and then use the features and then do some standard outlier detection algorithm on that. Could also use an autoencoder and then you could use the reconstruction error because obviously your autoencoder is trained on the majority data set. So if it can't reconstruct something, it might be something interesting. Yes?
So we have a lot of old data and we've now got a lot more sensitive equipment. So could we train some sort of generative model, a VAE, a GAN or something, to predict the new data that we observe given the old data, and then as soon as those predictions don't match, so using the discriminator output of the GAN or something like that, you can see that there's a deviation from what you're observing now.
Yeah. I love it. I had that idea the other day, and then I was really sad that there were actually already papers on it. But yeah, it's a great idea, right? You use a GAN that can generate the data, but then instead of using the generator, you use the discriminator and use that to look for stuff that's new. If it says, oh, this data is not real, but it actually is, then it just means something it hasn't seen before. Yeah, great idea. Anything else?
Aren't you then just assuming that your old data was treated perfectly, like that? Undiscovered. I mean, we don't really look at our old data.
Yeah, that's also true. And I mean, there's definitely, so for instance, these things definitely exist in some of the data that we have. We've already seen them, but there was a big discovery last year, but we just didn't know we had them. So that's also true. So there is a danger in being kind of too supervised, sticking too much to what we know. But it's a trade-off because we've got 10 million alerts a night. We've got to do something. We've got to filter somewhere. Any other ideas? Nothing exotic, crazy.
Maybe a slightly different approach.
Good.
I don't know how valid it will be, but I'll give it a shot anyway. So one of the things you're concerned about is obviously you're trying to discover things that are new. And at the same time, you're also making a lot of observations that are fairly common. So we were thinking of using something like EGM. And maybe what you do is you track, if you can somehow encode the transient data as maybe changes in state. So what is the likelihood that as time goes on,
Interesting.
spectrum will continue to decrease? And what's nice about doing that is, especially if you have a whole bunch of different models for how, like, say, a supernova event looks or how a neutron star merge looks, you can kind of build a hierarchy where, depending on the observations you make, you can pop down into each of the different flows, so to speak.
I like that because that really is very online. You start at the point where you say, okay, I don't know anything, and then you take a data point and you say, okay, given this data, I think it's most likely to be X, Y, Z, and I predict this to happen. And then something different happens, and you go, oh, okay, wait, no, I was wrong, it might be something else. So that's a very good way of thinking about it.
What's cool about that is, as you continue to make observations, you can continuously update your beliefs for how things should happen.
Exactly.
So it'll hopefully auto-correct as you encounter, or as the state out, either your tools improve or your observation, your underlying data.
Yeah, we'll have to do some mix of that and using a priori knowledge because you're going to have to do some pre-filtering anyway, given the volume of data. Very nice. Okay. Just some common approaches that wasn't mentioned, but there's a couple of techniques: isolation forest, one-class SVM. If you've got features that you think are reliable, then you could use one of these things, or local outlier factor, to look for outliers, or you could maybe combine it with your autoencoder approach. But to be honest, there hasn't been too much effort just yet into the anomaly detection astronomy. That's going to change very quickly, I'm sure. Okay, the fourth problem might surprise you that it's a problem. Source finding. You would think, as astronomers, we could find sources by now in images. If I have an image like this, surely I can be able to find these little blobs that are galaxies. So it's true, we have a lot of very standard algorithms for detecting sources in images, right? And a lot of them come from signal processing. There are algorithms the way you sort of expect. You look for peaks, you fit blobs to them, etc., etc. The difficulty lies in, especially in radio astronomy. Now, if you remember way back, I showed you the SKA, and it's made up of all of these dishes. You might have been wondering to yourself, how do you put this data? And it turns out to be quite a complicated process to put data together from different dishes and to actually make an image. What you can't see on this screen is that the background of this image is not really black. It's obviously got noise on it. And so what you can't see is that that noise is actually correlated, highly correlated. And the problem is that if you have a correlated bump in the noise, it masquerades as a source. So even the best source finding algorithms that we have are only about 10% efficient at the 5 level, which is really not very good. So this might be shifting gears a little bit, although you can definitely apply machine learning, and we have, to this kind of problem. But I just want you to think a little bit about how would you approach the source finding problem. And in particular, given the fact that we're never really sure we've got a source, so we really need to quantify the uncertainty. And that's what's kind of hard with some of the more traditional algorithms. So switch from machine learning more into statistics, more into probability theory, and try to think about, given an image like this, how would you go about finding the sources, and how would you go about quantifying your uncertainty about whether or not you've actually detected a source? Yes?
Is the correlation of the noise due to the instrument? So if you take an image of two patches of sky, will it be the same one over both?
So yes, it is due to the instrument, but no, it actually won't be the same because the instrument effects change depending on where you look in the sky. So it's basically just comes down to the fact that with like an optical telescope, you've just got one mirror observing the sky, so the noise is fairly well behaved. For a radio interferometer, you have to go through this huge, complicated process, getting from the raw voltages that come out of your antennas and turning it into an image. And basically, because you have gaps between your antennas, you have missing information, and it manifests as this extremely complicated noise structure. Yeah, so it is a tricky problem, yes. Talk to each other first, and then we'll come together and talk about that option. Okay, turn around and discuss. You got a couple of minutes. Okay, let's see if we've got any good ideas. I'm sure there's good ideas. Okay, hit me with your multi-wavelength idea. So that is something that you could do. So if you had optical data where maybe it's a bit easier to find objects, then you could at least use that as a starting point, right? The problem is, of course, sometimes you might have an optical source, but it doesn't have a radio counterpart and vice versa. So there'll always be some loss of objects there. But it's certainly a place that you could start. And for some observations, you may have multi-wavelength data. For other observations, you may not, right? Cool. Other ideas? Yes?
So if the noise is specific to the instrument as an assumption, could you decompose with some generated distribution of the noise to detract that from the image?
So this is actually already a deconvolved image. That ends up with correlate. This is a really hard problem. So what happens is, because your radio interferometer effectively takes a Fourier transform of the sky. Now every telescope does this, it just usually Fourier transforms it back. And that's where you get your final image, because it bounces off the mirrors. Radio telescope just does one, and then you have your Fourier data, and you have to do the Fourier transform to get into the image plane. But because of all your missing data, you end up with these horrible artifacts in the image, and you have to then deconvolve it. So this is actually already after a deconvolution algorithm called clean. I know. This is exactly why. So this is after 40 years, people are still using clean. Okay, we're gonna talk about alternatives soon. Don't worry. So yes, John has a very, very good reaction to how awful this algorithm is. And it basically, it's very difficult to replicate, because what people do is they do a whole lot of stuff by hand, make a whole bunch of choices, and so it's not like a nice, neat end-to-end pipeline, easy to model. So this is part of the problem that we're dealing with.
Sorry, I must interject at this point. What the radio astronomers should be doing is not trying to deconvolve data and give a single mode the best answer. They should be giving us a posterior distribution of what the answers could be. And then we can do realistic inference on that. And we know how to do this. Clean was obsolete decades ago.
Don't worry, I'll show you exactly that, which is a paper that we wrote a couple of years ago, which is very anti-clean. So, but before we get there, what you want is exactly what John says. You want something that gives you a posterior. So this is part of what I'm going to talk about in a little bit, but part of this algorithm that we developed is actually source finding. So in the contours, you see that this is the model source that we're trying to find, and this is running nested sampling, and so you can see that as it gets closer and closer to the peak posterior, it settles in on the correct position, the correct flux. We have to do this because there's always uncertainty in the positions and fluxes of these sources. So we really do need a statistical approach. And I'm going to mention that approach in a minute because it's very related. Well, actually, I'm going to mention it now because it's very related to my last problem that I want you to think about, which is high-dimensional sampling. Because what we did is we had exactly the same reaction to clean as John did. We thought it's awful. We thought, to be good scientists, what we should be doing is be working as close to the data as possible. So basically, to produce this image, you have to mangle the data a lot. So we thought, rather work close to the raw Fourier transform data, so work in the Fourier domain, not the image, and model the sky, right? So you can get a nice posterior over your model. And it looks a bit like this. This is the covariance matrix between the parameters of an example that we did. One of the reasons you want to do this is because instruments are imperfect. Particularly, there's something called a pointing error, where your antenna might be pointing. You might think it's pointing over there, but actually it's pointing a little bit off. And you can't always detect that. So that's a very common source of error in these images. But there's a lot of other sources of instrumental effects. And what you can see is that they correlate with the science parameters, with the things that you care about. Right? This is a problem. And when people do imaging, they deal with the systematics completely separately when they actually are correlated. So we have this technique called Bayesian inference for radio observations that doesn't do clean at all, doesn't go anywhere near the image plane, works directly in the Fourier domain, and actually models everything in a full forward modeling approach. Problems. The likelihood is slow. It's very difficult to compute this likelihood, although I must say to produce an image for MeerKAT can also take hours. So, clean is also slow. But anyway, the likelihood is slow, and dimensionality could be in the tens to hundreds of thousands range, because we have instrumental errors for each antenna, and we may have 1,000 sources, and we've got to fit parameters for each of those sources. So to do source finding properly, statistically correct, you end up with this very high dimensional problem that we actually are struggling to solve. Okay, because I'm running out of time, I'm going to give you guys about 1 minute. Just think about if you know something about how you could do sampling in very, very high dimensions, tens to hundreds of thousands of dimensions. Okay, I'm going to give you 1 more minute. Talk fast. Okay, your minute's up. Who's got some cool ideas? Especially stuff that I haven't heard about, please. Any ideas? How do you do high-dimensional sampling? This is a tough one. It's probably not one you can just work out. Anyone? Do you guys have anything? It's a hard one. Yeah?
Sampling like latent space in a very small temperature, and then just reconstruct a high dimensional.
So you're saying use a VAE in what? In the data? To compress the data, basically. Possible. I'm not too sure the likelihood computation will be any faster, though. Which is kind of where we're stuck. Anything else? Yeah? Effectively, yes. Yeah. Because what you can do is, in the Fourier domain, the reason why it's nice is everything is additive, unlike in the image plane. So if I simulate one source and another source, I can just add together the data, and I've got my two simulated sources. So, yeah? Yeah. Yeah. So that's exactly what we did. So I don't actually have a slide on it, but what we resorted to was a gigantic GPU cluster to do the likelihood computation, because it's a highly parallelized problem, because it's additive. So the GPU cluster computes the likelihood, and we used HMC to do the sampling. But still, for an SKA-sized problem, it took like a week to compute for 1,000 galaxies. So it's still an unsolved problem. So if you suddenly come up with any great ideas, please email me, because we still need to work on this. All right, so let me finish off in the last couple minutes. Basically, what I hope I've shown you in this talk is that astronomy is undergoing the same data revolution as everyone else, right? We're in the regime where we're dealing with terabytes, petabytes of data. We're needing to develop cool new algorithms to do stuff that would normally be done by a person. So it's actually a great time to be in this field, in astronomy as well as in all of your fields as well. I wanted to leave you with a provocative question. can machine learning do physics? So this is a paper, a very recent paper, a couple months ago by Tegmark. And I thought it was quite curious, so I'm just going to show it to you quickly. They made some simulations where they had different regimes with different physics going on in them. Okay. The upper left corner is a simple harmonic oscillator. This is a gravitational field in the bottom left. This is an electromagnetic field in the bottom right. Top right, there's nothing. In addition, there's a rule that if a particle hits a wall, it bounces. So you can see all these dots. So they start with some particle, launch it in, and then off it will go according to the different regimes which will affect its motion. So you can sort of see a sine wave here by the harmonic oscillator. You can sort of see it tends to fall down here by the potential well of the gravitational field. You can see it makes circles in this magnetic field. They constructed what they call the AI physicist, which is not just a convolutional neural network. It was basically a series of ways to make decisions. So to come up with hypotheses, they had this divide and conquer method where they come up with lots of different theories and then knock them out. They have a kind of evolving theory method. There was a whole bunch of different things that they tried. But basically what you're seeing here is the predictions of the AI physicist. So all it has is measurements. So it has some dots in this box, and it has to figure out the rules of the different parts of the box. So it has a classifier to figure out which part of the box it's in, so which rules should it apply, and that's the color that it gave it. And the size of the dot is basically the size of the error in terms of predicting the position of the particle. So you can see it kind of struggles a bit more on the edges, but does quite well in the middle. And when you look at the equations that it produces, they're very, very close, or if not identical, to the physics equations in these different regimes. So the question is, can machine learning do physics? I'm not going to answer that. I'm going to stop there and leave you with my email address. If you have any ideas about any of these problems, I would love to hear them, and thank you very much.